All right. So, are you ready for the next set? So, next big concept, random variables. So, we've been talking about events. What we're now going to introduce is a second step. So, we're going to assign to each element in our sample space a real valued number. So, this mathematically, this is written as x is a function that goes from the sample space to the real valued numbers. And essentially now we're introducing some quantities. So for example, we can look at a factory line and pick devices, check devices, and they're either faulty or they work. And x might be the number of faulty devices that we find in a day. Or we've got goat Dottie and we're milking her each day, then looking at the amount of milk that we get per day from goat Dottie. That's a number, it's a real valued number, but we're not, we can't, so it's just measurable, it's not countable. We could have a look at the height of NBA players. That's also measurable, not countable. Or we can have a look at the number of wins in a number of games. Let's say the number of wins in 5 games. Then we know that X will have the values 0, 1, 2, 3, or 4, or 5. So 6 different outcomes. So once we've got these random variables, we want to come up with essentially a table of how likely each one of the outcomes that X can take. So how likely each one of them is. So let's assume that we've got a discrete random variable. So we distinguish between discrete and continuous random variables. Discrete means we can enumerate, we can count the number of outcomes, whereas continuous means the outcome is measurable, but we can't count it. So let's have a look at discrete random variables first. And here we've got a special function called the probability mass function that tells us the probability for a single element in R. So X equals, let's say 3. The function px3 is then assigning a probability to how often we will see that outcome of 3. And all of the possible values of this table, of this function, is called the probability mass function. So the properties of this probability mass function is all of the values of this little px are between 0 and 1. And that's just because px is a probability and we've defined probabilities to be between 0 and 1. And the second property is that if we take all of the possible outcomes of X, so all of the possible probabilities, they will sum up to 1. So we have an outcome of our X, and if we take all possible outcomes, we're back to the full sample space. So the sum of the probability for the sample space is equal to 1. And that's the same for this probability mass function. The sum of all the probabilities in this probability mass function has to be 1. Let's have a look at an example. So let's assume that we're flipping a fair coin 3 times. So we've got possible outcomes as head, 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 tail, head, tail, head. So overall, we've got 8 outcomes that are all equally likely because the coin is fair. So now we can define a random variable, x, and let's say the random number, the random variable is the number of heads. So x is essentially counting how many h's we have for each element in our sample space. So x of this first element is 3, of the second element it's 2, the third element it's also 2, fourth element it would be a 1. So, and this is a typo. So here we've got a probability mass function. X is little x, where x is 0, 1, 2, or 3. And you can tell that these two guys here are supposed to switch places. This is supposed to be head, head, tail. No, tail, head, head. And this is supposed to be head, tail, tail. Sorry about that. I'll fix that and upload it to GitHub. So now we can count how many different outcomes we have for each of the different elements in X. So we have exactly 1 possibility to get 0 heads. We've got exactly 1 possibility to have 3 heads. For 1 head and 2 heads, we have 3 possibilities each. So overall, you can see that our 4 different possible outcomes of our random variable, 0, 1, 2, 3, 4, they add up to 1. So this is the probability mass function for a fair coin that's flipped 3 times. So how is that helpful? Now we can assume that we've got events. So for example, 2 or more heads. And the probability to evaluate these events is now just a mere lookup of the table values. So probability of x is greater than or equal to 2. So 2 or more heads is this plus this. So 3/8 plus 1/8 or 1/2. Probability of at least 1 head. So x is greater than or equal to 1. That would be everything here, or 1 minus no head. So overall 7/8. So those probability mass functions help us to make probability events that can be expressed in terms of this random variable to be much more manageable. So it's just another concept that allows us to capture chance a little bit more formally. And you can already tell that I messed up here, so I'm not great at listing these detailed sample spaces, and that's usually where I'm making sure that I'm using my computer. So R to the rescue, please. So there's a package called discrete RV that helps us to look into calculus with discrete random variables. And now we can define, let's say, a random variable. So let's say we've got a fair coin, and the code to define a random variable is RV, that's the function. The first set gives us the possible outcomes. The second parameter here gives us all of the different probabilities for each one of the outcomes. So I said this was a fair coin. So it should really have a head or a tail, but that is not a random variable. So sometimes we use random variables and events a little bit interchangeably. So let's be a little bit more precise. And this is we call this random variable fair coin, but what we really mean is throwing a fair coin and getting a head on this fair, so a head from a fair coin flip. That's this random variable. We've got a 1 or a 0 as potential outcome for we get a head or we get a tail, and each one of these outcomes has a probability of 1/2 because it's a fair coin. So now let's assume that we're flipping this coin multiple times. The call for that is IID for we're now implementing 2 coin flips that have the same distribution and they're independent of each other. So IID stands for independent and identically distributed, which is shorthand for something that we'll see later on. Here we use it as multiple flips of the same coin, and we're using so the second coin flip is not informed by the first coin flip, so it's an independent coin flip. So this gives us a random variable with 4 outcomes. So you can see that all of these outcomes are nicely listed, and we can also see that the probabilities are listed underneath. So we not only do we have a random variable, but we also have the probability mass function for that particular random variable, which means that if we want to have more flips, so here we're listing the fractions. We can set the fractions equal to false and just list the numbers. We can increase the number of coin flips. Here we've got 8 outcomes, and if you go into R and you use IID, you get this instantly, almost instantly, so you don't have to think about writing out all possible outcomes in the sample space. So it's a real huge time saver. So here we've got 3 outcomes. Instead of flipping multiple coins or just flipping multiple coins, we can also look at a summary. So here we're looking at the sum of 10 fair coin flips. So that is a random variable that just counts the different potential outcomes from 0 to 10. So we've got 11 outcomes. And you can see here that is again listed with all of the potential probabilities. And we didn't have to work particularly hard for this. So SOF stands for sum of IID. So we're summing over all of those fair coin flips. We've got 10 fair coin flips, fair coins that will be flipped, or one that will be flipped 10 times, doesn't really matter. And we can see here the probabilities from 0 heads to 10 heads. And what's also very nice, we have functions in discrete RV that look very much like the functions that we would use in math. So here we've got a large P function. We've got our random variable heads 10. We can check the probability for heads 10 to be greater than 3. So that would mean at least 4 heads, that we've seen at least 4 heads in 10 flips of a fair coin. And we're adding up the whole probabilities from 4 to 10. And we come out with the probability to see at least 3 no, to see at least 4 or more heads among 10 coin flips is 82%, 83%. Okay, so here we're still looking at probabilities that have even chance or are all likely. We can use the same setup to use in situations where not all elements in the sample space have the same probability. Trying to do this by hand is essentially resulting in disaster, at least for me. So try your hand at using discrete RV and have a look at this next your turn. So let's assume that, or no, not let's assume, tennis. So the Grand Slam means to win 4 major championships. It's actually the Australian Open, French Open, all of those. So there's 4 major championships in tennis. And winning all 4 of them in one season is the Grand Slam. So we've got a player, Djokovic. He's at the moment the top ranked male player in tennis. And looking at his performance between 2011 and 2019, he has won 15 out of these potentially out of 36 major championships. So we can assume, or let's assume, that Djokovic has a chance of about 15 out of 36 to win one of these major championships. So we want to set up a sample space for Djokovic's outcomes in one season. So assume that each season consists of exactly 4 major championships. Obviously 2020 is different, but 2020 is different for so many different reasons. We just don't count 2020 at the moment. And then we want to set up a random variable W that counts the number of wins in a season, in Djokovic's season. So next question is, what's the probability for Djokovic to win the Grand Slam? So winning all 4. You can do all of this by hand, but if you want to, try to use discrete RV. If you're still new to R, just have a look at the R code for Grand Slam and try to use it and try to work your way through it. All right? Let's set, I'll set up 5 minutes. Holler if you think that's too little. So 5 minutes. So let's have a look at the solution. And like I said, the solution is also in the R code. So just in case everything went a bit too fast right now, you can come back and get go through it slowly again. Okay, so let's just come up with some sort of notation. So D means Djokovic wins, L means he loses. So we can set up a sample space that essentially consists of all possible outcomes of the 4 major tournaments. So D, 4 Ds, that's the Grand Slam. Everything else is not the Grand Slam. So does it matter how many different outcomes we have? How many different outcomes do we have? So for each of those 4 steps, or for each of the 4 tournaments, we've got 2 possible outcomes if we just look added from Djokovic's side. So either he wins or he loses. So there's 2 for each of these tournaments, which means that we've got 2 times 2 times 2 times 2, 16 different outcomes. But not all of these outcomes have the same probability, right? So we said that Djokovic wins in about 15 out of 36 cases. So slightly less, quite a bit less than half. So we can set up a random variable, and let's call that random variable D, that has a 1 if Djokovic wins with probability of 15 out of 36, and it's a 0 if he loses. So now we go and we define the result from 4 of these matches, and we just look at how many of these matches Djokovic wins. So the sum of 4 repetitions or of those 4 matches. So 4, and we use the random variable. So that assumes that over the season, his winning chances don't change. So for every single match, he's in exactly the same shape, and he will win with a probability of 15 out of 36. So you can already see the limits of our hypothetical model here too. So this defines a new random variable wins. It should actually be W, but I'm good at reading and following my own instructions, so sorry about that. So this is the number of wins in those 4 matches. And we've got outcomes 0 to 4 with the associated probabilities given on our assumption of 15 out of 36 and 21 out of 36. And you can see here the outcome that Djokovic wins all 4 is about 3%, given his past performance in the last 10 years. So probability for the Grand Slam is about 3% based on that. I should ask, do you have any questions for right now? Okay. So next big concept. Are you appreciating why there were fireworks on the very first slide that I showed you? I'm very sorry. There's probably already coming steam out of your heads. I know there's some steam coming out of my ears. Okay, so expected values. What do we mean by an expected value? So based on the probability mass function of a random variable, what do we expect what is the expected outcome? So we can phrase this question a little bit bigger and answer it all in one go. So the expected value of a whole function of x, so function h of x, is defined as the expected value where we list all of those potential outcomes, multiply them with the probability in which this outcome occurs, and then sum over all of them. So the expected value is nothing but a weighted average. So the average outcome, so the outcomes are listed by h of x, and the weighting comes in through the probabilities. So one version of this h of x is nothing but the identity, so x itself. And that gives us the expected value of this random variable x. So the expected value of x is the weighted sum of all of its outcome. So weighted by the probability of each individual outcome. And sometimes we call this expected value of X also mu. I'm just a little bit more notation here. So what does that mean for a fair die? So let's just apply this particular function to a fair die. And I know that this is starting to get really abstract. So, but here we've got our probability. So probability that a 1 occurs, plus the probability that a 2 occurs, plus the probability that a 3 occurs. And we do that for all of the potential different outcomes that we have for our fair die, which means that the expected value of the outcome for a fair die is 3.5. So the outcome or the expected value is sometimes, or most of the times, it's not actually a real outcome. So it would probably make more sense if this was either a 3 or a 4, but the expected value is just a number, and it's the number that, and sometimes these numbers for discrete random variables are not part of the sampling of the sample space or the outcome of the variable X. So just to make you aware of that. So 3.5 only means that if we roll a die 100 times and we sum up over all of those outcomes, we divide by the number of rolls, then that number should be very close to 3.5. What does it mean for Djokovic? So how many tournaments would we expect him to win in an average year based on his performance? So the expected number of wins is 1.66. So 1 2/3. And obviously that's not something that that Djokovic can actually win. So it would mean that he wins more often 2 of the major tournaments than 1. And if we place 100 seasons and we look at the average number of wins, then that number should be close to 1.66. Assuming that his performance doesn't change over 100 seasons, which again is one of those, you can see the obvious limitations of evaluating these expected values. What I would like to point out here is E of wins, that's actually a little piece of R, which is why it looks so funny with the green here. I'm trying to show all of the results that we get from R as in this green color. So E of wins is an actual function call. Wins is the random variable that we defined earlier for the your turn. The capital E of wins is a function in discrete RV. And I just want to point out the similarity between what we do with the mathematical notation and then the function call in R. So discrete RV is trying to mirror the math notation as much as possible so that we can use it in R directly. Okay, so 1.66 is the expected number of wins in a major tournament. Ready for the next your turn? I'd be happy to explain things in case there's questions. All right. There was a question. No, not a question. Thanks. All right, your turn. A gambler's dispute. So this, we're going back to 1654. So a little bit of time travel. So the Chevalier de Mer was a really, really interesting guy. So French nobleman. also really interested in gambling and gaming, and he also ran a casino on the side, and a priest helped him run this. So very interesting times. So he posed this question: if he throws a pair of dice 24 times, should he bet on having at least one double six showing up in those 24 throws? So this phrasing of should one bet even money on at least one double six means that is the probability for a double six equal to at least 0.5. That would mean we've got a 50-50 chance of winning. So even money then means you pay in a certain amount to participate in the game, and you get the same amount of money back out. So you don't lose anything for sure. And hopefully you get a little bit more money out than you pay in. So should he bet on this double six in 24 throws? What do you think? So essentially what Chevalier is asking is, if each game costs $1 or $1, and he's going to win 2 francs for every time that there's at least one double six, but he will not get anything back if there is no double six. Should he make that bet? So is it lucrative? Is it good for him? So Chevalier de Mer had really famous friends like Pascal and Fermat, and he actually asked them in correspondence for their help on this problem, which led to a lot of formal notation of probability theory. So this Chevalier de Mer was very important in coming up with the theory for probability, but it was more his friends that were inventing or defining the concepts rather than de Mer in asking his questions. So I'll give you 5 minutes. Let's see whether you can answer this whether you can settle this gambler's dispute. Even money or not. And don't try to write it out in hand. Try to use R or read through R. Okay, my timer says it's time. So let's try to settle this gambler's dispute. Which side are you coming down on? No, yes. All right, I think we do have a dispute. Let's see. So we can. So when we can set up a random variable. Let's call that double six. And we already know that when we've got a pair of fair dice, and we're not going to consider any other cases. So let's say we've got a pair of fair dice. Rolling a double six is has a chance of 1 in 36. So we're setting up this random variable with 2 outcomes: no double six, yes double six, with these probabilities. And then we're using the sum of 24 rolls to count how often we do see one of these double sixes. And once we've got that, we can evaluate the probability of seeing at least one of these double sixes as greater than or equal to 1. So probability of 24 is now 0.49. So we see no double six with a probability of 0.51 something or 0.50 something, and a double six with just under 50% probability, which means that no, Chevalier de Mer should not try this particular game. We can bring the money in, and yeah, here we've got a random variable called Chevalier. He gets he pays in a -1 for the first event in those 24. That's when no double six happens, and then he gets a 1 back out in all of the other events, however many we have. So this is just silly R for, we take all of the probabilities of 24 but 1, and we repeat 1 for he gets a 4 back out. Or so he pays 1 in, he gets 1 out. Overall, we would hope, or he would hope, that he gets money out over time, but it actually turns out that he's expected to lose about 200 of a franc each time that he plays this game. So he should better not play this game very often. But it's a very small, it's a very small loss. But it's not even money. Even money would be if this probability is actually at 0.5. Okay? Does that make sense? The E is for the expected value. So that is that the E is one of the functions in discrete RV, and we just defined the expected value about 3 or 4 slides ago as the weighted average of all the outcomes that we potentially can have. So here we've got outcomes 1 and -1 with the corresponding probabilities. And overall, the expected value comes out as -0.017. That is in francs, so the same value as this random variable, Chevalier, paying 1 franc, getting 1 franc from a game. And the overall expected value is negative. That means that overall Chevalier pays more than he gets out of this game. So let's try another expected value. So let's say that in this particular game, the goal is to get as many chips as you possibly get. So you get a special card, and for this particular card, your chance to get a chip is 10%. So now you can, so you have 2 of these cards. If you have multiple cards, you can add the chance. So if you can decide whether you want to play 2 cards in one go and have 20% to get a chip, but only 1 chip. Or you can play the cards sequentially, one after the other, so have a 10% chance to get a chip, and then another 10% chance to have a chip. So strategy 1 is play the 2 cards sequentially. Strategy 2 is play the 2 cards together. which strategy should we use? What strategy would maximize our winning chances? So obviously strategy 1, the outcome would be either no chip or 1 chip. For strategy 2, we've got 3 potential outcomes. We've got no chip, 1 chip, or maybe 2 chips. So just in terms of the sample space, strategy number 2 sounds like the better deal. So what happens with the probabilities for each one of those? So again, I'm going to use discrete RV, so I'm going to use code to actually come up with those probabilities. So we define 1 card, or I should say a chip from 1 card, as the random variable of 0 and 1, where we have a 10% chance to get a chip. So then we can play 2 of these chips, 2 of these cards sequentially, and we get no chip, 1 chip, or 2 chips with these probabilities. So 81 out of 100, no chip, 9 or 18 out of 100, 1 chip, and 1 out of 100 would be 2 chips. So that's strategy number 1. The other strategy would be to play the 2 cards together, and that changes our probability from just 10% to 20% for 1 chip. So we've got 2 outcomes, 0 and 1, with 20% for 1 and probability of 80% for 0. So maybe by putting those 2 cards together, we essentially reduce our risk from getting no chip from 81 out of 100 to 80 out of 100. But at the same time, we're losing our potential chance to get 2 cards, also with 1%. So we're reducing our risk here by 1%, and we're giving up a potential bigger win, also with 1% chance. So let's compare the expected value. So we can calculate the expected value for 1 card. So playing 2 cards sequentially, or playing 2 cards together. And in both cases, our expected value is the same. So we expect to get, so if we play 5 times, we would expect to get 1 coin. What should we do? So I was talking a little bit about minimizing risk and maximizing our chances. But the expected value doesn't really help us in evaluating the situation. So instead, what we're going to look at is a different concept. So we're going to have a look at the variance of a random variable. And essentially, the variance of a random variable is measuring how far away, on average, we go from the mean that we would expect from this random variable. So the variance is defined as yet another expected value. So the expected value of this squared deviation of a random variable away from its mean. So how much spread do we have in this random variable? And just by definition of the expected value, what we do is we sum up over all of these squared distances, so xi minus this expected value squared, and we weigh that by the probability to see the xi in the first place. So what the variance then has the squared unit of what the random variable is measured in. So if the random variable is in francs, the variance would be in francs squared. If X is the number of chips that we get, the variance would be the squared chips, whatever that means. So this squared unit is sometimes a bit problematic. So lots of people look also at the square root of the variance. So sigma is defined as the square root of the variance, and it's called the standard deviation of a random variable. And now we're back to the original units. So the standard deviation has the same units as X. So how does that help us? We can again use another function, V, in discrete RV. So V of sequentially, so playing two cards one after the other, gives us a variance of 0.18, and playing together has a variance of 0.16. So we can actually see a difference between the two different strategies. The first strategy of playing one after the other has a higher variance than the second strategy of playing two cards at the same time. So that means that the variance is capturing what I said as minimizing the risk or maximizing our potential. If you think in terms of potential, then you want to have a large variance because we have more extremes. So our random variable goes further away from the expected value on average. If we want to minimize our losses, then we want to be closer to the expected value and avoid the risks of the extreme places, where we're thinking more of the extreme place in the negative way of no chip. And we're pulling our random variable closer to the expected value. So here the variance would be smaller. And I'm putting my question again. So what should we do? It's really up to you. In terms of the number of coins, we're not going to win more or less on average. So the expected wins are the same, but the probability to have more losses is minimized with playing both cards at the same time. And the potential for more gains is higher with a higher variance when we play sequentially. So it's really coming down to how risk averse or how risk happy you are. In German, there's a phrase, better the sparrow in your hand than the turtle on, not the turtle, the dove on the roof. You can go for the bigger with the more risk or the smaller one with less risk. It's really up to you. So I'll spare you this your turn. We can have a look at the variance and just apply the function of the variance. So this your turn is nothing more than an application of the definition. So we can just talk through the solution. So we've got we've got a fair six-sided die. The expected value of that is, like we talked about before, 3.5. The question is, what is its variance? So we've got the variance defined as the sum of all potential outcomes. We look at the outcome and its expected value. We square that difference, and then we multiply by the probability to see this particular outcome. So you can see here, we are listing all 6 potential outcomes, 1, 2, 3, 4, 5, 6. We subtract the expected value, we square that difference, we multiply that by 1/6. And that gives us a variance of 2.91. That's the squared units, so squared dots of a die. It might be easier to think of this in terms of the standard deviation, so 1.7. So what does that mean? How do we use the variance? And one of the main theorems in which we use the variance is Chebyshev's theorem. So a real theorem, mathematical theorem that tells us how to use the variance. So let's assume that we've got a variance sigma square or a standard deviation of sigma. And what this theorem says that is that the probability that x is less than k sigma away from its expected value, so absolute distance, so we can go both positive and negative away from the expected value, is greater than or equal to 1 minus 1 over k squared. So what does that tell us? It tells us how far away we, or how much probability we see for random variable x within a certain distance of the expected value. So we don't know anything about the probability mass function of x besides its variance. So we only know its variance, and we probably should better know the expected value of x, but we don't know anything about the specific probability. So we know expected value, and we can say that the probability to stay within a distance of k sigma from the expected value is greater than or equal to 1 minus 1 over k squared. So how much is that? So let's have a look at different values of k. So staying within 2 sigmas of the expected value has a probability of at least 75%. So if we say that we've got an expected value, say 3.5 for a fair die, plus minus 2 times the 1.71 that we just found. So 3.5 plus minus 2 times 1.7. The probability to stay within that is at least 75%. So similar, if we expand on the number of sigmas that we will allow, we can raise the probability quite considerably. So for any random variable that we know, literally any, we know that 96% of the probability are around 5 sigma of the expected value. So that doesn't leave that much probability for outside these spaces. So those are very rare occurrences that are outside a 5 sigma distance away from the mean. Okay, so we've been talking about discrete random variables, but all of what we were talking about with expected values and variances are also true for continuous random variables. They're just very slightly defined differently. So, continuous random variable. So we have something measurable in R. So for example, the height of NBA players or the amount of milk from a single goat. for each day. Then we can define the distribution function. So we define a distribution function instead of a probability mass function. So we define a distribution function f of x, or fx of t, as the probability to have at most t. So for Dottie, that, let's say t could be 10, probability to see at most 10 pints of goat milk is given as fx of t. So what, in order to make a function a proper distribution function, it has to be between 0 and 1. And given that this is a probability, this is going to be true. F also has to be monotone increasing. So that means that if we have two values, x1 is less than x2 or less than or equal to x2, then the distribution values, the probability to have at most x1 has to be less than or equal to the probability to have at most x2. And we also have to make sure that as t goes into the negative space, so it goes to negative infinity, this value is 0, and the probability that of fx of t when t goes to positive infinity is going to be 1. So essentially, we have a function that goes up in t. It goes up from 0 to a value of 1. And it always stays between these two values of 0 and 1. Those are boundaries. So that's a distribution function. Sometimes we're also talking about densities. And the density is defined as the derivative of the distribution function. So little f is the derivative of capital F with respect to t. And essentially what this means is that because f is monotone increasing, we know that little f is greater than or equal to 0 for everything, for every t, because it's just its slope. And what we also know based on this property here is that the integral of over all t's for this density is going to be 1. So for a continuous random variable, we've got two major functions. We've got the density, we've got its density, and we've got its distribution. Once we found a density, we automatically get the distribution by finding the antiderivative. If we've got a distribution, we can find the density by just identifying the derivative. So those two functions go hand in hand. And sometimes, and those two properties or sets of properties also go hand in hand. And sometimes it's easier to see the properties for the density. If they are fulfilled, then automatically all properties of the distribution function are fulfilled, and vice versa. So I'm going to spare you those proofs. What's important is that we've got a distribution function, which is a probability, a cumulative probability starting from everything that's negative up to this value of t. And we've got a density function, which is a value in t. It's a positive value. And if we integrate over all probabilities, over all densities, we get a value of 1. So if you think back to the probability mass function, the probability mass function is a little bit like a density function. But we can't define, why don't we just define a probability mass function for a continuous random variable? Like probability of x is equal to t. The reason why we don't do that is, so instead we define this density function. So the density function is actually very close to this probability. But the probability of x is equal to t is going to be 0 for every single t. And that's because we're in this space of real numbers. So t is actually one number with potentially infinitely many decimals. So rather than defining a probability that's exactly equal to 10, 0, 0, 0, 0, 0, 0, and so on, we define a probability that x is less than or equal to this t to avoid any complications from dealing with potentially infinitely decimal numbers. So distribution and density. Let's have a look at how that affects expected values and variances. And essentially it doesn't. If you think of replacing the probability mass function by the density function and replacing any kind of sums by integrals. So the expected value of a function of the random variable x is now defined as the integral over all possible values of x. So instead of the sum of the product of h of x times, originally we had the probability of this thing, of this event to happen. Now we have a density function. And we integrate over the space of x to get a particular expected value out. We do something similar for the variance of x. So the variance of x is just a particular case of h of x. So this is h of x. So h of x is x minus this, so the squared distance from the expected value, and we integrate over all potential values while multiplying. So while multiplying by the density. So again, a weighted average, because we know that f of x itself, if we integrate over it, that's just going to integrate to 1. So expected value is again a strange case of a weighted average of x, of h of x. Okay, so we get some math properties on how to actually calculate variances, because this integral sometimes is a little bit nasty. It might be easier to just calculate the expected value of x and the expected value of x squared, where we have x squared times f of x, and then look at this distance or the difference between the expected value of x squared and the square of the expected value. That's defined as the, if you do a little bit of calculus here, you'll see that this is going to be the variance itself. So let's do a very, very special case, but a case that we've been talking about already for a little bit. So a uniform distribution. So if we're thinking of any values in an interval, let's say we've got an interval of a to b, and we're picking a number, any number with equal chance, then we can define, so this is the definition of a uniform random variable or a uniform density. The density is defined as 1 over b minus a for any value of x that's in this interval. and it's going to be a 0 outside. So we've got this non-continuous function f of x, little f of x. It's 0 outside the interval, it's constant, and equal to 1 over b minus a for this interval. And if we look at the antiderivative of it, we get to a function capital Fx that's 0 up to a. Then it's a linear function that goes from 0 up to 1. So it measures the area under the curve up to a certain number. So we're at 1 at b, and then afterwards it stays constant, equal to the value 1. So what's the expected value in this situation? What's the variance? We use the definitions and we get an expected value of this x by integrating from a to b of x of f of x, x times f of x. So that's x times 1 over b minus a, so that's just a constant. So integral of x is x squared, and we put in the limits of a and b, so b squared minus a squared divided by b minus a, and once we simplify that a little bit, we come up with, well, it's half of a and b. A plus b over 2. The expected value is right here in the middle. So when we look at this, and I hope this makes sense. So expected value is right here. Expected value is actually the value along this x-axis. If you think of putting your finger as the tip of a scale, if you're putting your finger at exactly the point where this density function doesn't tip one way or the other, that's the value of the expected value. So we've got half of the probability mass function on one side, the other half of the density function on the other side, and here in the middle, this is the point at which things are stable. That's the expected value. And then the variance comes out as b minus a squared over 12, and that's just an application of some calculus. But that is true for every uniform density. So there's the standard uniform density that we oftentimes use when we're dealing with random numbers, random uniform numbers, where we're sampling on an interval from 0 to 1. And you can see that 0 to 1 simplifies a lot of things with b and a. So the variance would be just 1/12. And the expected value in that case would be 0.5, which hopefully makes complete sense. So if we sample randomly a number between 0 and 1, we would, our expected value is 0.5. So that's the point where we have 50% below and 50% above. Okay, I'll hand over to you. I've been talking a lot. So I'll hand over to you, and I'll give you, let's just try to keep it to 3 minutes. So I'll give you 3 minutes to investigate some of these functions in R. So in R, we've got sets of function that have the form R with a name, D name, P name, and Q name. So those X's could be the word unif, and then R unif, so random from the uniform is a function in R that will create n random numbers between 0 and 1 and return a vector. So have a look at how that works with 1,000 numbers. And then QUnif, have a look at what QUnif is supposed to do. So QUnif is the quantile function. You can have a look at question mark QUnif to see what QUnif is supposed to be doing. And it will allow you to double check the values that you get in the first set with theoretical values in QUnif. So 3 minutes, off you go. Okay, how did that go? We can have a look at these functions. I set a seed again, so if you're using a different seed, you'll probably get different answers. If you set the same seed and you run this code, you will get the same answers. So that's why I'm always reporting the seed whenever I'm using random numbers. So we're setting up a vector of random uniform values, 1,000 of them, with a minimum of 0 and a maximum of 10. And now we're just looking at a summary of those, and we see that, let's have a look at them from bottom to the end. So minimum is just over 0. And now I'm jumping to the maximum. Maximum is just under 10. So that's what we probably would expect to see. We see median and mean very close to each other, and hopefully really close to 5 as well, because that's what the expected value is supposed to be. Expected value is 0 plus 10 divided by 2. First quartile and third quartile should be 2.5 and 7.5. And the reason I know that is we can use the quantile function to come up with the theoretical values for these probabilities that correspond to minimum, first quartile, median, third quartile, and maximum. So the 0, 0.25, 0.5, 0.75, and 1. For a uniform random variable that's set up as 0 to 10, that gives these quantiles. And you can now see that the quantiles here match fairly closely to the values that we see. As long as we've got a symmetric density function, mean and median are the same. So that's why we're only checking for one value here. Does that make sense? Do you have any questions at the moment? So if not, we'll have a look at relationships. Relationships between random variables, that is, though. So let's have a look at what we can say when we've got two random variables. So what we're interested in here is we've got random variables, and now we're defining a joint distribution. So let's assume that we've got discrete random variables again, but it's going to be the same thing for continuous random variables, except we would have to deal with densities and integrals, and it's just a little bit less abstract when we deal with discrete random variables. So the joint distribution is defined as the probability that x is equal to little x, and at the same time y is equal to little y. So for the joint distribution of continuous random variables, it would be the easiest to just define the distribution of the joint random variables as the probabilities that x is less than or equal to little x, and at the same time y is less than or equal to little y. So, but that's it for continuous random variables. That's as far as I go with defining joint distributions. So let's have a look at an example. So the General Social Survey is a survey done by NORC, and they usually ask about 2,500 Americans about current issues. In 2016, they were asking participants regarding their happiness level, and people reported their happiness level in three levels: not too happy, pretty happy, and very happy. So let's say that we've got the two variables, random variables, gender and happiness. And we're looking at the breakdown for the results from the 2016 survey. So we can then come up with a joint probability mass function for G and H by looking at the overall sum of these, by the number of participants overall, and dividing these values by that overall number of participants. That gives us the joint probability mass function in here. So 9% of women reported to be not too happy, 7% of men did so. 31% of women reported to be pretty happy, 25% of the men, or 25% were men reporting to be pretty happy. So we've got a couple more numbers here on the outside, and these values on the outside are called the marginal distributions. And you can see exactly why they are called marginal distributions, because they are in the margins of the joint probability. And here the marginal distributions are nothing but just the individual, the distributions of G and H by themselves. So this is the probability mass function for happiness overall, and this is the probability mass function for gender overall. So we see that in our survey, 55% of the respondents were women and only 45% of the respondents were men, which is why we see that women and happiness always seem to have higher numbers regardless of the happiness level. That's because we've got more women in the sample overall than men. So we were talking about independence of events. Now we can extend this concept to independence and random variables. So does it matter whether we have a woman or a man regarding their happiness levels? So we define two random variables to be independent if every single of their elementary events are independent. So a random variable is independent of another if all of its sub-events are independent of that other variable. So the probability that the joint event of X and Y is equal to the product of the individual probabilities for all possible scenarios of X and Y. So in the example, let me come back to that. In the example, we want to know whether happiness is independent or dependent on gender. So we're checking whether the probability, the joint probability is the same as the product of those margins. So that's why I came up with those margins. So now we're checking whether for each cell, whether the element of the cell is equal to the probability, the product of the marginal probabilities. So 0.09 is that equal to 0.16 times 0.55. 0.07 is that equal to 0.45 times 0.16, and so on. So let's check that for, so we compare those by calculating the differences, and obviously we're not going to see exactly the same numbers. So what we see here is 0.09 and 0.087, 0.31 and 0.309. The question is, are these differences similar enough? Or are they really different enough to show that there's a real dependence between gender and happiness? So what do we mean by similar enough? So for that, we do a test, and this test is called the chi-square table test of independence. And very generally, we have two discrete random variables. We assume that X has capital I different levels and Y has capital J different levels. We assume that X and Y are independent. That's our null hypothesis. So that's our working assumption. Our working assumption is these two things, these two random variables have nothing to do with each other. They're independent. And under that assumption, we get expected values. So we would expect, if this null hypothesis is true, that the value in cell little ij, so the probability that X is I and Y is J, that's given as the margins. Oh, come on, what happened now? That's given as the product of the margins. That's our expected value. Compared to that, we've got an observed value, little o ij, where ij is the cell I. So X is I and Y is J. So we're looking at the difference between what we've observed and what we would expect under the null hypothesis. We square that difference, we divide by the expected value, and then we sum over all of those cells. So that gives us one value that tries to combine all of the deviations that we see across all cells. So it's one number, and that one number is called the test statistic. So that number is going to be fairly high if there is a big deviation between observed values and what we expect the values to be. And it's going to be very small if all of the observed values are close to the expected values. In that case, that number is really close to 0. Otherwise, it can go to wherever. So there's no limit on it. So a lot of math tells us that this C follows what's called a chi-square distribution, which means that we might not know its exact value, but we know its overall shape. And this chi-square distribution has a parameter C that's given, that's called the degrees of freedom of this table test. And it's given by the number of different levels that we have in X and Y. So it's given as I minus 1 times J minus 1. That's the degrees of freedom. So in our case, we have 3 happiness levels and 2 genders. So C is going to be 2. And we can run this test. Actually, we can use R to run this test. And for gender and happiness, there's absolutely nothing there that would make us reject the null hypothesis that gender and happiness are independent. So let's have a look at a different example, and I'll hand over to you again for a couple of minutes. Let's do 3 minutes again. And you can have a look at happiness level, whether happiness level and age are related in some way. So here's a frequency breakdown for age in just 2 categories, below 60 and 60 and above, with corresponding happiness levels. So this gives us a joint probability mass function. So try to come up with all of the relevant numbers. So this is a lot of number crunching. Or you hop into R and you let crunch for you. So try to come up with the chi-square statistic. And then you can compare your chi-square statistic to these values. So 2 degrees of freedom, chi-square for a chi-square distribution means only 10% of all values will be higher than 4.61. Only 5% of all values will be higher than 5.99. And only 1% of all values will be higher than 9.21. So let's evaluate the happiness level. I'll give you 3 minutes aren't really realistic. Let's aim for 3 minutes and see how much more you need. So let's start with 3 minutes. Okay, how did that go? You need more time? We can also have a look at my R solution. I cheated a little bit, so it's going to make things a little bit easier going forward. So let's maybe focus on that. So the results for this general social survey are actually available in various different packages. So here's one package. We're looking just at the 2016 values, and we can have we can introduce a variable that we'll call age 60 as age is less than 60. And for the moment, I want to not deal with any kind of missing values, so I'm leaving out any kind of missing values. So then we can run a chi-square test by just giving the function chi-square test the 2 variables that we want to test on, age 60 and happy. So if we look at the frequency breakdown, we'll come up with the table that you've seen before. the chi-square test here gives us a chi-square statistic, a C value of 6.97. So did some of you get this? 6.97 as, yes, Grayson, thanks, 6.97. That's based on that frequency. So how do we interpret this? We've got 6.97. 6.97 falls in between these two numbers. And that means that 6.97 is among the numbers that show up less than 5%. So in less than 5% of the cases, but more than 1% of the cases. So it's an event that happens quite rarely. It happens with a probability of 0.03. And in this case, we would say that we would reject the null hypothesis that happiness and age are independent, and say that there is some dependency. So one question was, characterize the deviation from independence. And for that, we really have to look at the individual levels. And that's something that my solution here doesn't provide with us. So I would need your help with that. So where do we see values that are too high? And where do we see values that are too low? So if my memory serves me right, we've got more people 60 plus reporting to be very happy than what we would expect, and fewer people under the age of 60 reporting that they are very happy. So fewer than we would expect based on the number of cases that we have with age less than 60 and above 60. But I could be wrong. So if that is not what you've seen, please let me know. So that's one thing that the test cannot tell us. We can decide to either reject or not reject a null hypothesis, but very rarely does the test actually tell us why. So that's something where we would usually use visualizations. And in the code, there is a line that will show you a visualization of this frequency table, but I don't want to go and explain mosaic plots in a lot of detail right now. Okay, so we reject the independence between age and happiness level, and all look forward to being a lot happier when we're age 60 and above, right? Okay, so I said I would come back to some properties of expected values and variances. And again, this looks very abstract, but this is actually very applicable. So we've got two random variables, and we come up with a linear combination, any linear combination of these two random variables. So the most general way that we can write a linear combination of x and y is to say we take a times x and we add b times y to it. So that's a new random variable. Let's call it z. What can we say about the expected value of z? And the thing is that we can do the same thing with expected values that we did with the random variables themselves. So the expected value of z is nothing but a linear combination of the expected values. So A times the expected value of X plus B times the expected value of Y, that's going to be our expected value of Z. So an expected value is just keeping it's just a linear function in its random variables. So it's super easy to work with. The problematic case is really the variance. So the variance is a stinker. The variance is not particularly nice to just scalars. So when we have the variance of a random variable X and we multiply that with a value, the variance of this multiplied function random variable is a square of the variance of the original random variable. So scalars are squared, which also means that if we look back at the standard deviation, we can fix that. So the standard deviation of A of X, the standard deviation of A of X is equal to A times the standard deviation of X. The problem is we can't fix things when we have summations involved. So the variance of AX plus BY is equal to the sum of the squared scalars times the variances. So A squared variance X plus B squared variance of Y, plus essentially what boils down to a mixed term. So plus 2 times A times B times the covariance of X and Y. And we define the covariance of X and Y as the expected value of X minus, of the product of X minus EX times Y minus EY. So that's called the covariance. And if you think back of how the variance was defined as the expected value of the squared deviation of a expected value, it's no wonder that this looks a bit like a square. So we've got the square of one element plus the square of the other element plus the mixed term of those two elements. So that's a definition of covariance. So covariance is probably something that you haven't seen as much, but correlation is definitely something that you've seen before. And the thing is that correlation is nothing but a standardized form of the covariance. So we take the covariance and we divide by the square root of the variances. So covariance divided by square root of variance of X times the variance of Y. That is the correlation. And we have a couple of properties that we know about the correlation. Correlation is between -1 and 1 for all random variables. And if X and Y are independent, then the correlation is going to be 0. The problem is the other way around, it's not true. So we can have cases where the correlation between X and Y is 0, but X and Y are not independent. Let's have a look at, that's the reason for that is the correlation coefficient is measuring the amount of linear dependence between an X and Y. So it might be that we're in a case where the linear dependence is actually 0, but there might be other dependency, some functional dependency between X and Y that the correlation coefficient is not able to identify. So let's have a look at some situations and for relationships in X and Y. And let's have a look at how that boils down in correlation. So the top line shows scatter plots of X and Y with correlation coefficients that you might expect. So if we've got a perfect line, correlation is 1 between X and Y. If we've got more and more scatter, the correlation coefficient goes down. And then we change the directionality of the linear relationship and we switch into a negative correlation. And with a -1, we've got a perfect negative relationship between X and Y. So essentially Y is equal to some negative X plus something. That is a perfect negative relationship, so with a correlation of -1. So what does that mean in terms of the slope? The slope doesn't factor in at all. So correlation is always 1, independent of the slope. So correlation coefficient is not equal to how steep this slope, how steep the linear relationship is. Correlation is not defined if we have a flat line. That's because the variance in Y is 0, so we're dividing by the square root of 0. As soon as we've got a negative slope, we have a negative correlation, and the correlation is -1. Maybe most surprising is this line at the bottom. These are all situations in which X and Y obviously have some functional dependence, but the correlation coefficient in all of these cases is 0. So a correlation coefficient of 0 doesn't mean that we have no relationship, so independence like we would have here. It just means that we don't have a linear dependency between X and Y. So keep that in mind when you're looking at correlation. A correlation of 0 does not mean that we're necessarily in this situation. It could be one of these situations as well. So bottom line is always look at scatter plots too. So another thing that I would like to say at this point is we have to be really careful about how we express things. So very rarely does statistics allow us to make any inference on causal relationships. So we can say that as X increases, we see an increase in Y. But what we cannot say is that Y increases when we increase X. It's a very subtle difference, but the difference is that we can't assume that there's a causal relationship between X and Y. We can only observe co-occurrence. Somebody else has to decide on whether this is actually a causal relationship. In statistics, we can only observe co-occurrence. So as X increases, we see an increase in Y. As X decreases, we see a decrease in Y, but not necessarily a causal relationship. So here's, for example, some numbers from the National Survey of Drug Use and Health for 6 regions in Iowa. And what we can see here is alcohol use in the past month. This is the percentage of respondents who had some alcohol in the past month. And on the y-axis, we have responses that of participants that reported to have binge alcohol use in the past month, so above a certain quantity in alcohol, different for men and women. And what we see is, we see generally a positive linear relationship, particularly strongly if we don't look at central, but even with central, we have a positive linear relationship between alcohol use in the past month and binge alcohol use in the past month. That does not mean that increased alcohol use might lead to binge alcohol use. The pattern that we see here is just one of co-occurrence, but it's very tempting to say something about increased alcohol use might lead to binge alcohol use. And it might even be true, but from a statistics point of view, we cannot decide on that. Just a small different case of perception of greater risk of having 5 or more drinks. So perception of risk of what essentially is the definition of binge alcohol use. And binge alcohol use in the past month. And it seems that there is, so if we don't regard Northeast, we might see not a very strong relationship between binge alcohol use and perception. If we include this observation of the Northeast, we have a negative correlation. So as the perception of greater risk increases, binge alcohol use decreases. But you can also see that this hangs very dramatically on whether we include or not include this element in the Northeast. And we have to decide whether this is an outlier and should not be regarded, or it should be regarded. And again, this goes above the pay grade of a statistician. This is where we would need to ask experts for a potential explanation of why this value is so much higher than any of the other values. All right. Do we have questions at the moment?